So it's a pleasure to have Jianqiao speak on Whittaker categories of your algebras.
Yeah, thanks for the introductions. And it is exactly the correct order I'm going to talk about. So yeah, indeed, talk will consist of two parts, and the first part is about Whittaker categories. Doesn't have to be related to W-algebra. It's defined for all categories C, X G, and use this notation G of K for the loop group. So K is and also O is the integer. So for any category C, is the action of GK. And well, in fact, later we'll also add double kappa, but well, now it's just a category with a loop group action. Typical example will be the modules on a space X, and where X has the action of GK. And another example, in fact, more important to us is the category of Kac-Moody algebra modules. Okay. So we have, so what are these Whittaker categories? Have we fix T and also Borel. So there are unipotent radical N, and you have the Whittaker character. So N and commutator. This is a billion group, the derived sum of the simple roots. So for each simple root, it's GA, and we have the residue map just the coefficients of the 1 over T. And polynomial element AN Tn to A minus 1. And this Whittaker character and K is just sum over all residues over the simple roots. GL. Simple.
Sum of GA, you mean like algebra of GA?
Yeah, each G alpha is GA. Whatever. The one-dimensional additive group and coefficient system. It's an IND scheme. That's very important. So from this character, you also have this exponential modules coming back. Sometimes I will call this alpha sign, go back. Or the exponential D-module or the Artin-Schreier sheaf depending on coefficient.
It's really cyber shriek, right? I mean, sorry, doesn't really make sense.
Please correct me. Yeah, Yeah, so Whittaker invariance of C will just be NK sign invariance of C. But there is a little bit ambiguity here. Sometimes people also write this for the co-invariance. It is true for a group scheme that invariance and co-invariance are the same. But here, NK is not a group scheme, it's an int scheme. However, there is a functors by Skryabin. This co-invariance. There's a functor from co-invariance to invariance, and it's in fact an equivalence and will be proved there. There's a more constructive definition of Whittaker invariance. So this is a int scheme and it's a limit of some pro-unipotent groups. So say NO. So this is a pro-unipotent group, and let's fix Rorschach dominant code. We can consider, well, we can consider this group at minus n Rorschach code. The dominant, well, the sign here, well, n is an integer. The sign here is to make this thing gets bigger and bigger, and in the limit will become NK. But the point is, these groups are of pro-unipotent group schemes.
Rorschach to be like to have some positive roots, or just you're saying any dominant co-weight?
Yeah, it is. It is the half sum of the positive co-roots, and in particular, it is dominant.
Probably also important that it's regular, right? Like,
yeah, it is. Yeah, it's regular dominant. Yeah, it's true that if you choose any regular dominant co-weight. And this Whittaker C is then the limit of each this group. Yeah, there's a remark here. Psi is a character of each of this for all n in character.
limit or a co-limit?
Co-limit for the co-invariance.
So I see.
Yeah, and yes. So each of this is this pro-unipotent is also
Yeah, right.
equal to its co-invariance. And if you take the co-limit, that will give you the Whittaker co-invariance.
Transition functors are say this. Sorry.
Yeah, I will. In fact, I will use another set of groups, and I will define the transition matrix. So NK. Right. So limit. Well, first you can write co-invariance here, and it's a function. Well, okay. So in fact, although these are perfect pro-unipotent groups, they are not open compact subgroups of G. We will use another sequence of groups, subgroups. Maybe so. Okay. The so-called adolescent Whittaker categories. So these are defined by invariance of some open compact subgroups. Subgroups are use this notation IN circ. So these are first you have O. So I write this way to have a clean formula, but it means that after mod Tn, the group is your element is upper triangular. It's less than n. This is a normal subgroup of GFO. And then we further conjugate by this minus n row check. So if you look at this group, the upper triangular part will get bigger and bigger, and the lower triangular part will smaller and smaller. And the typical example, when n is 0, it is just beautiful. And if n is 1, the thing inside is just Iwahori. But you also, the pro-unipotent radical of the Iwahori. Maybe the circ is referring to, and conjugate to the pro-unipotent radical. If n is greater than 0, all these groups are pro-unipotent. Yes, you didn't miss that. I'm going to give some examples of this group IN. Then G is GL2. It's IN. Or just the elements are just 1 plus TNA. So 2n. It looks like this. Notably, the diagonal parts also decrease and it's larger. And also, they don't have the same relative dimension. Groups become smaller and smaller. When E is GL3, IN is maybe 1 plus Tn. A, B, C, D are power series. Here is T minus n minus 2n. The lower triangular parts are. And there is a remark. So although they get smaller, there are no inclusion relations between these groups. So IN is not included in IN. First. In fact, if you compare when n is smaller than n, compare IN and IN will have more roots on the positive direction and less roots in the.
All those TNs should be multiplied by some power series.
Yeah, it should be multiplied by
Yeah.
O, but I just ignored this. And it's quite maybe convenient to introduce this number is 2 row check. It is also the dimension of add and well, or in fact, it's also the sum of I/2 for the fundamental exponents. But it's some quantity, and in fact, that's the relative dimension. So I am n is smaller than m. I am quotients. I am interest. I am. That dimension is m minus n. This adolescent Whittaker category is then defined as invariance under this open compact subgroups. Psi is still a character of each IN. And there are relations between this have the functor I and M star from C IN circ if n is smaller than or equal to m. First, you forget the intersection and then average. Star average. Here. And also there are the other direction from IM to IN. It's the same function. But the reverse direction. And note that these two are not adjoints. And they give the connecting morphisms that you can define the Whittaker invariance as the limit and colimit.
What was the problem with these systems? Why do we change it from these groups to?
They are not open compact subgroups of G.
Sorry?
They are not open subgroups of G.
Oh, okay.
These connecting morphisms, they satisfy some commutative diagram. IN sub psi. IN star. So you can forget to the intersection with NK is exactly that. And also average here. Here, the vertical arrows are forgetful functions. The limit in the bottom will give you the Whittaker. invariance. So we have a map from the limit in I and M star. And similarly, using the shrink, we have the limit of this CIN or baby Whittaker, adolescent Whittaker. The main theorem maybe of the first topic. Well, this notation is smaller than or equal to n may suggest that it gave you a filtration of the Whittaker category. And this main theorem says this is basically the case. So let's allow m to be infinity. In this case, I infinity is just efficient. The main theorem says for each of this shrink pullback, they do have left adjoint. I and M shrink. And also these are fully faithful. As long as n is greater than 0. And also this shrink are like morphism are the same as star. So I and M shrink is I and M star up to a shift. So the second part says Whittaker smaller than equal to n. Categorical C. And you take m to be infinity. Let's call this IN shrink. IN shrink. IN infinity. This is fully faithful. And if n is smaller than equal to m. And when n is smaller than m, it's also faithful, fully faithful. Okay. So this degree shift in particular says if m is infinity, then everything here lies in degree minus infinity. So before I actually prove this, maybe talk about the finite analog. So these are all.
Sorry, I'm just a little confused by this board. So I think the Whittaker invariants are the co-limit under the star functors. So I think you just want to write co-limit there, right? Sorry, the co-limit under like the averaging functors. The limit under forgetful functors. Like if I have this group n of k, right, it's approximated by all of these conjugates of n of O that are getting bigger and bigger. And so if I'm taking the invariance for this big subgroup, it'll be like the intersection of the invariance for all of these subgroups that are approximating it, right? So it's a limit over the invariance for these compact open subgroups where the transition functors are forgetful functors.
Transition functors are not.
So in the limit here, right, in the first expression, in this limit, the transition functors are forgetful functors. The co-limit, the transition functors are averaging functors, right? So I think this expression will be, in order for this expression to be correct, you would either have to change a couple of things, I guess, like you wrote co-limit and then change the right side to co-invariance, then it would be correct.
Are you saying this? That makes.
Yeah. I think it's correct. Yeah. Yeah, I think it's good now.
Okay.
This one is the more counterintuitive one. The limit is more intuitive, right? Because it's just saying like the invariance for this big subgroup is the intersection of the invariance for these subgroups that approximate it. And this is like the dual thing. It's a little bit less.
But this is a nice one.
Yes. Sorry, and then on the top right board, what is width of C?
So if you have this main theorem, then you show that Whittaker invariance and the co-invariance are the same. Here it means invariance.
Invariance.
The functor is when m is infinity.
Exactly. Yeah, so what's going on is if you replace this diagram with the I and M upper shrieks, right? If you replace the I and M lower stars with I and M upper shrieks and the averages with forgetful functors, then that gives you a functor from the limit under the upper shrieks, right, to the invariance. And that's the statement is that's an equivalence. And then when you pass to left joints, you get this expression for invariance as a colimit, which is what you're claiming here.
This third part basically says this shriek average is the same as star average up to a shift. This comes from some cleanness property. We talk about this finite setup. So we say, so whenever you have a open scheme 0, there is an open embedding and f p prime p0, then we say f is clean. The shriek extension is the same as fine extension. But there is always such a canonical match, but it clean is an isomorphism. Usually, let me explain the setup of classical canonical, Braverman and published. It says if X is a B variety, B now it's finite. And that U minus is the opposite. Important radical. And psi is a Whittaker character on U minus. So then the following is X. And embedding from U times X to G. And for any sheaf on X, and the Whittaker demodule on U, so psi, upper shrink down psi. It is clean. The shrink extension is the same as the star extension. Maybe I should explain why I choose such a setting.
You mean like
U minus.
say shrink pullback of the exponent or something?
Yeah, that's it. We are interested in this sheaf because if we want to consider the Whittaker average, so average star of F. This is indeed, there is an action map A, just a star push forward of maybe also up to a degree shift dimension, or in their setup is dimension of U, and average shrink is the same thing but replaced with the shrink push forward. So, the cleanest basically says this shrink average is the same as the star average. And because this is right T exact and left T exact also means the average is reverse T. Okay, so how is this cleanest proof in this case? In fact, we only need to prove the case when X is a point. So in fact, claim the Whittaker of G mod B, or the sheaves which are U minus and psi equivariant, it's just fact. Or in other words, sheaf here so only supports this single U minus orbit. So that's why if you take the extension, everything in the closure automatically vanish. Has to support on this orbit. So this statement is for just the stabilizer. So if you have sheaf supported on this orbit, if omega, if this W is not identity, then it must make some negative simple root to positive one. So then there exists alpha I positive. And then this the one-dimensional group corresponding to this simple root acts trivially on this point. But the character psi is non-trivial. This orbit cannot support any u minus psi aggregation. So only the open orbit can support and the Schrick and the star extension automatically agree on this open orbit. Well, in our setting, we need to replace this U by NK, which is an in scheme. But the argument also, it's also similar. Now, let's look at the theorem proof. The theorem part 1 for M is infinity. When M is infinity, it means you can Schrick average with N with C. In other words, we need to define this if let's say if this category C is just the X, then we consider similar setups and K. INs. Because with N there is a IN in action appearance. So this is the action map. And we want to define the Schrick push forward of the Whittaker box product with any F. Yeah, so we still have some compactification. This case, NKIN. So this is the same as beautiful. Well, okay, let me introduce another notation. G of ON is just a conjugate of G of O, like this, and row check. And then NK intersect IN. This is the same as NK intersect G of O. The positive part of IN is the same as the positive part of G of O, because before the conjugate, it only modifies the things in the lower triangular parts. And now you can further include this NK all. Its closure is an improper subscheme of the affine cross-binding. These are all improper. And the map from the closure you consider this map, it makes sense to say that act shrink is act sum. It's improper. So it remains to show that this J is a clean extension. The argument is basically the same. The other orbits in the closure cannot support any very invariant sheaves. So there is a lemma. So instead of quotient by G of O, in fact, it's given to the quotient by some congruence subgroup. Where this Kn is the nth congruence subgroup of G of O. This upper script n, the same thing, you just conjugate by rows. The proof is to consider the closure of the semi-orbit. Everything below the open orbit will cannot support Whittaker invariant sheaf. Okay, UFO closure is lambda this way. Lambda is this. Okay, so this means the closure in affine Grassmannian and go back to group. So if lambda is not zero, so we can find a root alpha I such that lambda alpha I strictly negative. And then if you consider this one-dimensional group, T inverse alpha I. It acts trivially on this points because when you pass through T lambda, the exponent is becomes -1 minus lambda alpha I, which is greater than 0. goes to G of O n. In fact, it lies in N of O conjugated by T lambda. N of O is a subgroup of Kn. Like it acts trivially on T lambda, but T lambda cosine. However, this character psi is non-trivial. Yeah, so this lemma basically proves the cleanness of this embedding. So we can define a shrink average to Whittaker. And you remember the definition of INM upper shrink, first given by forget, and then you star average. And its left adjoint from so this is helpful functor. And this average star has a left adjoint, which is just forgetful functor. And this forgetful functor also has a left adjoint given by the shrink average. Thus has a left adjoint in lower shrink. And in fact, IN shrink is given by a kernel. The convolution with this function Kn is object. On the right hand side is okay. Wait.
It depends on your conventions. It's
Yeah, okay.
that's
Anyway,
important.
because I want so this sheaf is supported on NK IN. And in fact, our premise says, well, yeah, it is not supported on the whole closure is just a orbit. We take the one-dimensional D-module on this orbit and the star or Schritt extension. And then we want to show that IN Schritt are all polyphasical. It suffices to prove this is the identity. So this is the isomorphism. The unit. Unit. Of the junction. Or in other words, for any sheaf F, because all these functors are given by kernels, let's say IN upper Schritt is given by kernels delta IN Schritt. It is supported on INs. So want to prove this isomorphism for all sheaf F. F as in C IN. Hi. But in other words, F is the same as this convolution with IN. So yeah, so it suffices to compute this object and a conjugated by delta. So this we want to prove the right hand side is the right. Both sides are objects in this bi-covariant category. And psi, and so this left-hand side is supported on IN, so well, the unit double coset. And the right-hand side is supported on IN times NK IN. The argument is also similar to previous ones. So everything in. So this is true because we have shown that KN is supported on NKIN and not in the closure. So theoretically, this object is supported on its image in GK. Well, take the product. So the point is every element inside this product, if it is not in IN circle, then cannot support by equivariant sheaves. In some sense, the relevant double cosets are only INs. This is the lemma. So if G is the element in NK, and the character of psi is the same as IN at IN. Then G has to lie in I. The condition here means this double coset IN circ GIN can support a bi-equivariant sheaf. Psi has to be the same stabilizer. You want to see the proof of this lemma? Okay, then let's just ignore it. Well, it's some theoretical computation.
So we should take a break soon.
Yes. So yeah, so let me briefly mention that once you have the Foley faithfulness for IN shrink when M here is infinity, then for INM, this follows immediately for more reasons. Because with N, C have this composition. This is IM lower shrink. Shrink. And this composition is IN shrink. And the top arrows just compose well. So IM shrink is fully feasible, so you can define INM lower shrink by just go through bottom row and then go back to M. Yeah, so the third point is also a similar argument. It's some cleanness, and the only difference is there's a degree shift from the relative dimension of IN and IM. You can take a break. So now we're actually going to talk about W-algebras, which I know even less about. Yeah, so the main goal is the following theorem called affine Skryabin theorem. The statement is similar to the finite case. Says the following two categories are equivalent Whittakers of this Kac-Moody algebra modules and modules of the affine W-algebra. In this affine setting, both sides, we talked about the left-hand side. But both sides are more complicated, and there are subtle issues in even defining the right DG category, the right-hand side. So first, from our previous results, we can say that the left-hand side is compactly generated. It's not obvious this affine setting. So we have that is compactly generated. And in fact, because it's a limit or co-limit of this with n, each of this embeds fully faithfully into the Whittaker category, and each of this is compactly generated. But in fact, it's generated by this object induced module from the algebra of IN. So, this character psi. This is a compact object and generates this category. But if you take this as a hint, before proving this theorem, okay, so after you have this theorem, you can say that they also give you a family of compact generators of the W modules, W algebra modules. I consider the image of objects. By the way, so this is induced, but this is compatible with the semi-infinite cohomology functor. So we have consider this map. Here I'm viewing this as a co-invariance. Let's just forget the algebra structure. So this should be the semi-infinite cohomology functor psi, which talked about in previous talks. Like this.
What's the functor in Skryabin theorem?
I haven't defined the functor yet.
Oh, wait, you define psi to be this composition.
No, so this psi is defined from here to here.
Yeah.
So this is a composition. So this should be the semi-infinite cohomology functor psi, which talked about in previous talks.
Okay.
So this I'm saying that this equivalence compatible with this semi-infinite. So both sides have this compact generators. So say this more precisely. Yes, so yes, G so this functor psi, it actually factor through the Whittaker category. So this functor I will denote by psi width. And this is true because we can, so there is a definition, but in the definition of this functor, you can view this as a co-limit of average, taking the homology for this minus a rho, and all. The same sign. And this functor will automatically factor through average of this group, and when you take the co-limit. There are some strange effects on the weight n. Because they are fully faithful inside the Whittaker category, they also have this functor to fact. The following diagram also commute. So that's both are psi width here, I and m star are average. But in fact, we want to use the shrink because you can talk about an infinity shrink. Doesn't make sense. The shrink average, there is a shift. This is psi divided by minus 2n delta. And so this theorem is proved by first proving some abelian categories equivalence. Well, this really depends on some construction of T structures. This is what I'm going to talk about next. The T structure. So there is a canonical T structure on with smaller than equal to n. Because these are just modules. There is a canonical T structure by forgetting the equivariance. However, these T structures are not compatible. You actually need to shift it by something like n delta. The canonical T structure. Or in particular, this object, the induced module. Psi lies in the heart. In heart. Okay, so there is a lemma for the connecting functors from n to m. There are two functors, I and m shrink and I and m star. But if you shift it here by minus f minus n delta, then it's the same as I and m star shifted by m minus n. So this connecting functor is T exact for this T structure. That's basically because this thing has negative homology degrees and this thing is positive ones, and so because they are equal, exact. So then there are some normal consequences that you can glue this together to get a T structure on Whittaker category. So we view this with G hat kappa. This is the colimit of this I and M shrink listed by this M minus N. So basically, I am using the same I and M shrink, but intertwined with the auto-equivalence on each with N, which just shift by degree N delta. And theorem, there is a unique structure on this bit such that all this embeddings I and lower shrink. If you shift it by n delta, this is T exact. And further, this bounded below part is just a derived category, but the bounded below part in the derived category of the heart. That's the theorem which is very formal one. Consequence of these things and all the polyphasicalness of connecting functions. So that's basically the left-hand side of the affine Skryabin theorem. Yes, so we have said the compact objects are induced from the algebras In, but in fact, we are going to use to take care of the degree shift as well. This object, WKN, defined by induced it's basically the induced module, but also need to twist by some line bundle. And shifted by this degree n delta. So what is this line bundle? Ln is the determinant line bundle of minus n row check. Oh. Main thing is the degree shift. And there is a prime here, so this is actually not W-algebras on the Kac-Moody side. So it doesn't lie in the heart of weight n, but if we consider In shrink, so this embeds into Whittaker category. It does lie inside the heart of this Whittaker category, because In shrink twisted shifted by n delta is the exact, and this thing is in the heart of weight n. They are the families of compact generators, and in fact, we will still use this notation to denote embedding. The main reason of introducing this twist, in fact, this functor psi Whittaker is co-represented by this pro object. They're also connecting morphisms.
I guess another way to say this, the twist makes these compatible under the I and M lower shrieks.
Yes.
Right.
Yes. You mean which twist?
This twist by this line. So like when I apply I and M lower shriek to that thing, I get W prime M.
Right.
Like that's what you mean by these assemble into a per object?
Not really.
No.
There are morphisms I haven't defined. But there are WKM to WKN.
Okay.
Alpha and M. This is also it's epimorphisms. And each wk prime n co-represents the functor from which n to vect. Yeah, so what does this wk n co-represent? Represents a functor sustaining f to the cohomology and infinite. Not just cohomology. The algebra of IN and twisted by a line. IN. It's plus and delta. Okay, there's no problem. So this will map to the intersection of IN with NK is this group. You can forget the algebra. That is actually by Whittaker of just IN shrink F. There is a rate shift by minus 2n. So if it is if this is plus n delta, then it is just semi-infinite cohomology. But it's minus n because we have a n delta shift on this object. But I erased the commutative diagram, and this degree shift happens to be the one we use for the side weight. So these true objects will co-represent this functor. Like width. That's basically the Kac-Moody side. So WK mod, right? We also have compact generators. It's also compactly generated. Well, in fact, it's built in the definition. We'll first have this elements WKN, which are there is a lemma. When you apply the functor sign to W prime n, it is concentrated in degree 0. I see not back. And we'll define this WKN to be the Deros cohomology of this thing. they are compact objects, so compactly generated. They are compact. When n is 0, this is just simply WK, the usual W algebra. Here, WK prime 0 is the usual vacuum module. In some sense, this WKN are generalized vacuum modules. So how is this category defined? The WK mod. Well, first you can define the Billion category, modules of WK. And then the bounded below category of this part contains compact objects. So WK mod C. This is a subcategory, full subcategory generated by all these compact objects. WKN. And you can also add shifts and clones. And then WK mod is taking the completion of the compact. So maybe if I write this way, there is not so illuminating, but maybe I can talk about some properties of this WKN. Maybe let's recall there is a so-called constant okay, filtration on WK0 or WK, so that is associated graded is the functions on F plus E. Important by N. So this N also have compatible mutations WKN. Now the functions are T minus N and minus N. This it's still a closed subscheme of F plus E. All these are closed like here. Right, so if kappa is infinity, then W infinity N is actually regular functions on Hopper's G-check with singularity less than or equal to N. So these are these are Pauling space by enroach somewhere. This guys. Um, so now to prove the affine Skryabin theorem is just on the abelian category level, there is the following general theorem. So if A is a abelian category and F functor from A fact abelian category functors before abelian category. Any problem?
No, I think it's okay. Sorry, just custom filtration.
If you have a functor like this, is here exact or is exact and preserves co-limit. Then in fact there is a equivalence A to and F mod. What's wrong about awesome filtration? Yeah, so you have the functor of this, and here the functor is psi with. If this functor is co-represented by a pro-object, so if F is co-represented by some objects an, pro object pro algebra pro object, then and F is the same as the pro vector space you evaluate at F at an. This is and we know psi Whittaker is co-represented by those objects at WK and prime. Whittaker, the abelian category is equivalent to some modules. These algebras are in this case just WKN. It's pro object, so it agrees with the category on the W algebra modules. And then you know both sides are compactly generated. Maybe another consequence of the theorem is So now you have proved. And as we know, this is by the Feign Frenkel duality, this is also is the correct notation. So if you have the Feign Frenkel duality, there's W algebra for G and K, and same as W algebra of GD and double K. And this is also Whittaker of well. So you automatically have this equivalence of the Whittaker category. If K is the critical level, then you get the Whittaker category of a smoothie algebra is the same as a quasi-coherent sheaves opers of GD. Because this case is just regular function sample. Yeah, so these are categories over Q code. So on the right hand side, you have the substack given by slope. The slope smaller than or equal to n. You consider weight of n on the left hand side. That's exactly corresponding to the pullback phase change. But yeah, the statement is they are sheaves supported on opers is singularity, that's something. I can stop here. Bernie.
Sorry, could you explain how to construct the functor in Skryabin's theorem?
So we use this categorical, well, here basically it says the endomorphism is the W algebra, the pro object WKN. This gives you the functor.
And what was the functor on the Boolean category?
Semi-infinite cohomology, right?
It is, yeah, essentially semi-infinite cohomology. But in fact, it's basically unique. It's determined by knowing the compact objects are sent to WKN, and then you know how to compute the endomorphisms.
Other question? I think Jianqiao